Welcome to The Explainer. Today, we're completely reframing how we look at math. We're literally pulling geometry out of those dusty textbooks and putting it right where it belongs, in the physical world all around us. We aren't just looking at abstract numbers and lines today. We're looking at the actual structural blueprint of everything from skyscrapers to snowflakes. Because if you really want to understand how the universe is built, you absolutely have to understand its building blocks.
Okay, let's dive into this. Think of this explainer not as a boring math lesson, but as a cinematic journey into a master builder's blueprint. The source material we're looking at today fundamentally frames geometry around one really cool core theme: understanding how shapes are built. Every single object you interact with, every building you walk into, relies on the hidden rules of these structural components. So we're going to put on our hard hats and deconstruct these shapes piece by piece.
Here's our quick roadmap for today. 1. The power of polygons. 2. Decoding triangles. 3. The world of quadrilaterals. 4. Circles, the perfect curve. And finally, 5. The beauty of symmetry. Let's get started.
Section 1. The power of polygons.
Now, before we even define our very first shape, look around the room you're in right now. The walls, a book, a window. You are surrounded by flat shapes. And most of those fall under one massive geometric umbrella: the polygon. A polygon is defined simply as a two-dimensional shape made of straight lines. I really want to emphasize that absolute fundamental requirement: straight lines. If it curves, it's out of the club. Polygons are the rigid, straight-edged frames of the geometric world.
And by simply adding more of those straight lines, we build incredible complexity. The basic families include triangles with 3 sides, quadrilaterals with 4, pentagons jumping to 5, hexagons with 6, all the way up to octagons with 8 sides. It's kind of like upgrading a structural frame. The more sides you add, the more complex the polygon's properties actually become.
Section 2. Decoding triangles.
Since you can't enclose the space with just 2 straight lines, the triangle with its 3 sides is where geometry truly begins. Let's move to the triangle and see how this builds. Now, what's really interesting about this slide is how we classify these shapes, almost like a geometric detective identifying suspects. You can identify a triangle by looking at its sides or by looking at its angles. On the sides front, we have scalene with absolutely no equal sides, isosceles with 2, and equilateral, where all sides are perfectly equal. But if you look at the angles, you might find an acute triangle where all angles are tiny, under 90 degrees, or a right triangle featuring one perfect 90-degree corner, or even an obtuse triangle, stretched out with one angle greater than 90 degrees.
But here's the heavy, unbreakable rule of the three-sided world. No matter how you stretch, squash, or skew a triangle, whether it's scalene, right, or obtuse, its interior angles will always sum up to exactly 180 degrees. It's a universal constant in the blueprint of geometry, which is exactly why triangles are the most rigid and reliable shapes used in bridge and roof trusses.
Section 3. The world of quadrilaterals.
All right, let's step up the structural complexity to a 4th straight line. Here's a practical challenge for you. Look around you again and see if you can spot exactly 5 rectangles. I guarantee they're holding up the room you're sitting in right now. Those rectangles are just one piece of a larger family of 6 major quadrilaterals we need to know: the square, rectangle, rhombus, parallelogram, trapezoid, which is also known as a trapezium, and the kite. Classifying these is all about asking 3 critical structural questions. Do they have equal sides? Do they have parallel sides? And do they have right angles? How a shape answers those 3 specific questions completely determines its identity.
Let's contrast 2 that often get mixed up in the geometric lineup. A rhombus is basically like a square that's been pushed over. It has all equal sides and opposite parallel sides. But a trapezoid? It only has one single pair of parallel sides. Parallel lines are the ultimate deciding factor here. They totally change the structural integrity and the classification of the shape.
So, the crucial point is, when we upgrade from a triangle to a quadrilateral, we aren't just adding a side. We're doubling the structural capacity. Because you can essentially fit 2 triangles inside any 4-sided shape, a quadrilateral contains a massive 360 degrees of interior angles. It's literally just 180 times 2.
Section 4. Circles, the perfect curve.
We are officially leaving the rigid, straight-edged world behind and stepping into the infinite curve. To understand the circle, you have to know its vocabulary, which is beautifully anchored visually right here. We've got the center point O. The diameter, line AB, cuts straight across the middle. And the radius, like line OC or OD, stretches from the center right to the edge. The source material suggests a fantastic real-world activity. Take a standard dinner plate, measure its radius, and use that to predict the entire outer boundary of the plate.
And this brilliantly illustrates the connection between our curved shapes and our straight shapes. Look at the lines here, AB, BC, CD, and AD. These are called chords. By using these chords, we can actually perfectly inscribe polygons, like these triangles, totally inside the boundary of a circle. So the straight lines and the perfect curve aren't enemies at all. They actually fit perfectly together.
To calculate that outer boundary, the circumference, and the internal space, the area, we rely on the absolute magic ratio of pi. By multiplying our radius or diameter by pi, we can translate this infinite curve into actual, real-world measurements that we can use to build and engineer things.
Section 5. The beauty of symmetry.
We've talked a lot about the building blocks, but what actually gives them visual balance? Symmetry. Symmetry manifests in 3 distinct transformations. We have reflection symmetry, which is like a mirror image right down the middle. We have rotational symmetry, where you can turn a shape a certain number of degrees and it looks exactly the same. And point symmetry, which focuses on matching everything symmetrically through a central origin point. It's the ultimate balancing act in structural design.
And you know, this isn't just some abstract math concept cooked up by humans. Grounding this in reality, nature was the very first architect to utilize these symmetrical blueprints. Just look at the perfect reflection symmetry of a butterfly or leaf. Look at the rotational point symmetry of a starfish, or the incredible repeating hexagonal polygons of a honeycomb.
Our source material challenges us to create a literal shape museum out of our everyday surroundings. So I want to leave you with this provocative thought to ponder. If geometry really is the hidden blueprint of everything from massive skyscrapers down to tiny snowflakes, what unseen shapes are holding together the room you are sitting in right now? Take a moment, look around, and see the architecture of the world with totally fresh eyes. Thanks so much for exploring the blueprint with me.